Before electronic computers, people built mechanical computers to perform specific mathematical operations. One such machine was this, Albert Michelson's Harmonic Analyzer. This 19th century machine adds together cosines to create intricate patterns. Amazingly, it also does the inverse operation. It can take a pattern and reveal the cosines that, when added together, will approximate it. This operation is called Fourier analysis and is possibly the most important mathematical technique of the past 100 years. Without Fourier analysis, there would be no MP3s, JPEGs, or cell phones as we know them today. To celebrate this stunning machine and to gain a greater insight into what Fourier analysis is and how it works, I'll share in this video some history of this analyzer and then in 3 additional videos detail its operation. In synthesis, I go step by step and examine the key components of the machine and how each plays its part in adding cosines. In analysis, I show you how the machine uses the same mechanical motions to find the frequency components of a signal you want to analyze. And in operation, I show the steps an operator of this machine must go through to perform these calculations. This machine's designer, Albert Michelson, was famous for measuring the speed of light, yet he also measured many other properties of the universe precisely, like the diameter of stars or the rigidity of the Earth. In the late 19th century, he performed Fourier analysis by hand to help resolve fine details of the light emitted by vaporized elements. He was doing an early version of Fourier transform spectroscopy. These hand calculations were laborious, so he invented this machine to automate these calculations. He built a prototype machine similar to this one in 1897, and then a larger prototype 4 times the size a year later. The machine was then commercialized by William Gartner and Company. They made precision scientific instruments often designed by Michelson. In their 1904 catalog, they advertised this machine, which can add up to 20 different sinusoids, as well as a larger version that calculated with 80 sinusoids. We know that in the early 20th century, Gartner sold at least 4 of these machines, and based on that, it seems this 20-element machine sold for around $225, and that it was likely made between 1901 and 1910. After this period, the machines are mentioned only occasionally. We found pictures of several different configurations until it made one last public appearance in an improved form at the 1933 World's Fair in the Great Hall of Science in an exhibit called The Magic of Analysis. Our machine has an unknown history. We're not sure when it arrived here on the University of Illinois campus. We only know that for at least the last 40 years, it is set in a glass case in Altgeld Hall, its gears completely still. Join me as I bring back to life this stunning mechanical computer. I'm Bill Hammack, the Engineer Guy. This astonishing machine uses just gears and springs to add together sinusoids. This synthesis, as it's called, creates beautiful patterns that look nothing like sinusoids. The machine produces patterns like beats, smooth peaks, sharp corners, or even jagged edges. And these can all be made using this function. Here's how this mechanical marvel implements that function. The machine has 5 key sections. First, a crank that varies x. Second, gears and cams that generate frequencies. Third, just a little bit above that, rocker arms that create the sinusoids, and amplitude bars to weigh those sinusoids. Fourth, at the top, springs and levers that add together these weighted sinusoids. And lastly, on the front side, a mechanism for recording the sum on a piece of paper. At the heart of the machine lies 2 sets of gears. This cone-shaped set has 20 gears that vary linearly in both size and number of teeth. It engages the cylindrical set of 20 gears, all of the same size. Watch what happens as I turn the crank. The gears on the cone-shaped set all rotate together. The gears on the cylindrical set can rotate independently, each at a rate determined by the corresponding gear on the cone. This gear rotates twice as fast as this gear, this one 3 times as fast, and so on. These gears generate the different frequencies. A cam on each gear drives the rocker arm up and down via a connecting rod. As each gear rotates, the corresponding rocker arm traces out in up and down or a sinusoidal motion with the same frequency. For example, the first rocker arm oscillates to produce cosine 1x, the 10th produces cosine 10x, and the 20th cosine 20x. Of course, the arms in between produce cosine 2x, 3x, 4x, and so on. At the bottom, a series of long vertical bars rest on each rocker arm. At the top, these bars attach to levers that are spring-loaded. The position of the rocker arms on the bar determines the coefficient. As I slide this bar to the edge of the rocker arm, the lever at top rises. That's a coefficient of plus 10. When I return it to the rocker arm's pivot, the lever returns to its original position, a coefficient of 0. And as I continue to slide to the opposite edge, the lever drops, a coefficient of minus 10. Now, let me show you how the machine sums these sinusoidal motions weighted by their coefficients. I'll set the machine up to produce beats using sine 12x and sine 10x. Each lever at the top of the machine has a spring that connects it to a pivoted bar. A large spring balances the pull of the series of springs on the levers. If we look at the top, we see the spring extends more than a foot above the machine. As I turn the crank, the amplitude bars drive the spring-loaded levers up and down. This in turn moves the pivoted bar. Because the springs all pull on the same pivoted bar, their displacements are summed. If we take a close look at the pivoted bar, we see that it sweeps out a small arc. We can barely see it go up and down. Let's return to the front to see how the machine amplifies this motion and then records it. This lever magnifies the result from the summer, but it's still a very small motion. A wire connects the magnifying lever to a set of concentric wheels that amplify further the motion. This wire pulls on the hub of this inner wheel, while a different wire is wrapped around the outer wheel. The wire attached to the larger wheel moves the pen vertically as a set of gears connected to the crank has been moving the paper horizontally under the pen. This is the same crank that rotates the gears to create the sinusoids and that also moves the pen up and down. Amazing as that synthesis is, that adding together of sinusoids, the machine does something even more fantastic to me. Given any periodic function, it will calculate the correct mix of sines or cosines needed to synthesize that function. Understanding that process, called analysis, will, in the next video, enrich our understanding of the machine by looking at its operation from a different point of view. I'm Bill Hammack, the Engineer Guy. In the previous video, I showed how turning the crank on this machine generates 20 different frequencies, also known as harmonics, which are turned into cosines here, multiplied by coefficients, then summed, magnified, and the resulting function plotted here on the front. This process is called synthesis. But this machine is called a harmonic analyzer, which means it can be used to solve the much more difficult inverse problem called analysis. For example, if I want to plot a particular function here, how do I set the amplitude bars to produce it? To illustrate how this machine does analysis, let's start with a square wave. First, we use some unique properties of the square wave. Since it's periodic and even, all of the information that function carries is contained in half a period. So we'll take that half a period and sample it at 20 equally spaced points. We use the values of these points as the inputs for the machine. When we turn the crank, we produce a new function that reveals the correct coefficients. To see how we get these coefficients, we'll look at the side of the machine. As I turn the crank, the tips of the rocker arms form a sinusoid. The indices on the rocker arms run from high on the left to low on the right. I'll flip the video to make it a little more intuitive. When the rocker arm tips are lined up in a straight line, we'll call that crank number 0. If the horizontal axis runs from 0 to pi, and the vertical axis from -1 to +1, then we can describe the position of the rocker arms with a cosine. Every 2 turns of the crank increases the frequency of the cosine by 1. At these even-numbered cranks, the values of the function on the platen yield the coefficients we're looking for. Let's rewind and watch the plot and the rocker arms simultaneously. If we pause briefly at every second crank, a point is marked on the function. We create a total of 20 points. If we look at the output from the machine and compare it to a sync calculated by a computer, we see that they are very similar. Now, we'll take the data points from the sync, scale them, and use these values on the rocker arms. Remember that our goal is to program the analyzer so that it will plot a square wave. Now, as I turn the crank, the pen writes a horizontal line, then drops and writes another flat section, which amazes me because we're adding only cosines. And then it rises to write another horizontal line. Of course, what we're seeing is a square wave. What I've just shown with the machine is an essential feature of Fourier methods. I can take a function, perform harmonic analysis, extract the coefficients, and then synthesize that function to approximate the original. So, now that we see that this machine can do harmonic synthesis and analysis, I'll show you in the next video some details about how to set up the analyzer to perform these calculations. I'm Bill Hammack, the Engineer Guy. In this video, we concentrate on the machine itself, how to set up, adjust, and calibrate the machine for use. Let's look at the 5 main things we can set when using the analyzer. The amplitudes of the sinusoids we're summing, the horizontal scaling, the vertical scaling, choosing sines or cosines, and lastly, adjusting the pen so it writes correctly. Let's start with setting the 20 amplitude bars. As we saw in earlier videos, this lever's position on the rocker arms determines the value of the coefficient. We set that position precisely using this tool. It's a small brass bar with an adjustable stop. The brass bar has markings that go from 0 to 10 in increments of 1/10. The stop slides along the bar and can be fixed at precise points. Here we slide the stop up to 5, place the tool on the rocker arms, and push the amplitude bar into place. When I slide the stop all the way up to a large number, like 10, I slide the amplitude bar out to reach the end of the tool. Recall this measuring stick goes from 0 to 10. So how do we set negative amplitudes? We set the measuring stick to the magnitude we want and use it on the opposite end of the rocker arms. On the left are the positive coefficients, and on the right side are negative coefficients. The amount of horizontal scaling depends on how fast this platen moves as the crank is turned. The platen can move slowly, at a medium pace, or very fast. This gear train that moves the platen consists of these 6 gears. The first gear is on the shaft of the crank. A chain connects this first gear to the second gear, which you can see up close here. On the same shaft is the second gear, and sitting just behind it is a third gear. It has 12 teeth and engages the fourth gear. This fourth gear has 120 teeth. Behind and attached to the fourth gear is the fifth gear. This gear has 12 teeth and engages the rack, which is the sixth gear. You can see from the back how the rack runs the full length of the platen. I can adjust the horizontal scaling by changing the first and second gears. First, remove this tapered pin and pull off the crank handle. Next, unscrew the nut that holds the other gear in place, and then unlatch this gear system so it disengages from the rack. Here's the same motion, but from a different angle. Notice how the chain is now slack and so can be removed. The machine came with 4 gears, 1 small, 2 medium, and 1 large. I'll remove a medium gear from the crankshaft and replace it with a small gear. And then replace the medium gear above it with the large gear. Then affix that gear with the nut, replace the chain, attach the handle, secure it with a pin, and then relatch the gears. Now, let's look at 3 gear combinations, large and small, medium and medium, and small and large, and see how each translates the platen. I'll start with the large, small gear configuration. When it reaches halfway, I'll start the medium gear set. Notice the pins move up and down in sync. When the first gear set is 3/4 of the way, I'll start the third gear set. They finish all at the same time. This large-small gear set yields twice as many periods as the medium gear set. And the small-large yields half as many. In contrast to the horizontal scaling, the analyzer uses a different method to scale up and down. At the top of the analyzer, the vertical scaling is determined by the magnifying lever. This cylindrical rod extends from the pivoted summing bar. The position of this knob on the lever determines the vertical scaling of the output. When the knob is toward the end, the amplitude is at a maximum. When the knob is about halfway, the amplitude is reduced. And when I place it all the way inward, the amplitude is at a minimum. A second rod perpendicular to the first controls the vertical offset of the output. This knob slides up and down, and the wire wrapped around the end connects the rod to the inner hub of the magnifying wheel, which in turn is connected to the pen. Let's look at the pen and the knob simultaneously. We'll mark the current position and move the knob up. Notice a small movement of the knob yields a large movement of the pen because a set of concentric wheels connect the wire attached to the knob and the wire attached to the pen. The diameter of the outer wheel is 5 times that of the inner wheel, and so the pen moves vertically with 5 times the magnitude of the knob's motion. We can set the analyzer to use either sines or cosines. We do that by configuring these gears: the cone gear set, the cylinder gear set, and the pinion gear. Recall that when we use the machine, the gears on the cone set engage the gears on the cylinder. To change between sines and cosines, we need to disengage the 2 sets of gears. Unscrewing this knob allows the cone gear set to swing away from the cylinder. You can see it more easily from the top. This action completely disengages the cone and cylinder gears. Notice that each gear has a notch and can be rotated independently. The goal is to put the sinusoids associated with each gear in phase. You can see that sinusoid's motion from the side. As I rotate the gear, the rocker arm above moves in sync. Internal cams drive the connecting rods up and down. When the notches are aligned, the cams and the connecting rod are also aligned. Aligning the notches is a bit tedious, but it only takes a few minutes. Once they're aligned, I can position the gears for sines or cosines by engaging the cylinder gear with this pinion. This lever pushes the pinion into contact with the cylinder gear set. Notice the notch. When all the notches are in this position, the machine is set for sines. If I rotate the gears 90 degrees, this sets the gears for cosines. Again, if the notches are on the side, the machine calculates sines, and if they're on top, the machine calculates cosines. Why is this? When the notches are at the top, the rocker arms are at their maximum travel. That's like a sinusoid starting at its peak, which is equivalent to a cosine. When at the bottom, the rocker arms are at their lowest point of travel, which is like a sinusoid starting at its trough. This is like a negative cosine. And when the notches are on the side, this is a middle position, which is equivalent to a sine. If we set the amplitude bars for a square wave and set the machine for cosines, we get this even function. It's even because it is mirrored around the y-axis. And then keeping the amplitude bars the same, but setting the gears for sines, we get this odd function. It's odd because it's rotated 180 degrees about the origin. The output of the machine is recorded by a pen mechanism. This brass pen holder, which looks authentic, was made in our shop because the original is long lost. A long square brass rod rests gently in an open bracket, its top attached by a wire to the outer rim of the magnifying wheel. I attach the pen to this brass block. A square rod with a cylindrical end fits into the block and a set screw secures it. A removable rectangular frame secures the pen to the brass block. Here I attach the frame, insert the mini Sharpie pen, and secure it. I orient the pen about 45 degrees against the direction of travel of the platen, and then press it up lightly against the paper. As I turn the crank, the pen smoothly writes the function. Oddly, if the pen is perpendicular to the direction of travel, the plot tends to have flat peaks and troughs. And if the pen is oriented with the direction of travel, it's even worse. This particular machine, with gears to produce 20 frequencies, was likely built around 1915 and is a descendant of the first analyzer that Albert Michelson ever built. He used what he learned from that first model to construct an 80-gear machine and even planned to build a model with 1,000 gears. What a wonder that machine would have been. I'm Bill Hammack, the Engineer Guy.